Song from the Department of Electrical Engineering and also the Graduate Institute of Communication Engineering at National Taiwan University, located here. And he's a scientist and an engineer in quantum information frontier. And currently he is holding two major titles. One is the Yu Shan Scholar, the other, Yu Shan Scholar is sponsored by the Ministry of Education, and the other is the Einstein Scholar, sponsored by the Ministry of Science and Technology, meaning that his kind of annual income is more than most of us. That's why he's here today. And one of the reasons. Okay. So he got his bachelor degree, first degree here in the Department of Electrical Engineering at NTU, and then he moved on to do a joint PhD degree from both the Graduate Institute of Communication Engineering at NTU here and at the Center for Quantum Software and Information at the School of Software at University of Technology Sydney in Australia. Right, and then after the joint PhD degree, he moved on to England, to Cambridge, for his postdoc. So the first part of his postdoc was sponsored by the Ministry of Science and Technology. That's at the DNTP. That's where I got my PhD. So DNTP stands for the Department of Applied Math and Theoretical Physics. And at the same time, he was affiliated with the Darwin College. So his main research interest includes the quantum information processing, the quantum communication, quantum machine learning, statistical processing, and the matrix analysis. So today he's going to talk about a very sexy topic, which is taking place, but with a lot of degree of freedom. In the near and the long future, there's a combination of quantum science and also the machine learning. So his title is Quantum Machine Learning. So let's welcome Professor Zheng.
OK， 我是都可以。那我们就讲英文，好。OK， 好，应该有吗？我问一下。
Anyone here who cannot understand Mandarin? 全部都听得懂中。You don't understand Mandarin, right? Okay.
Okay, thanks, Professor, for this very kind introduction. Okay, today, because there are many students from different various fields, so I will only give an introduction to this quantum machine learning. And what is quantum machine learning is the main goal of this talk. Okay, I will refer to many literature and papers during the talk, so please feel free to take notes if you want to dive in the field of quantum machine learning. Okay, so firstly, I will talk about various models for quantum machine learning, and then the two main topics we are going to talk today to speed up the implementation of a machine learning algorithm and to learn with quantum machines. Okay, so what is quantum machine learning? So I will first give a very broad definition for this, and I will give a more precise definition for myself in the end of this talk. So we know that quantum information science is a very rapidly developing field from 80s, and there are many directions like quantum communication or quantum computing from this quantum information science. And we also know that the machine learning is a big group, and there are many applications everywhere. So roughly speaking, quantum machine learning is kind of an intersection between these two fields, and how they interact with each other is the main goal of this talk. Okay, so why are we studying machine learning and quantum machine learning? Okay, firstly, quantum information science has demonstrated many advantages in several fields. For example, in computation, there are many quantum algorithms that can speed up certain computational tasks where there is no competing classical algorithms. For example, like the integer factorization problems. Right now, the fact is classical algorithm is like exponential time, but Peter Shill's algorithm can provide a polynomial time quantum speed up. And in communications, we can use entanglement to increase the channel capacity. So essentially, you can have faster transmission rate. And also, quantum communication allows qubit for transmission, whereas we cannot use any classical communication method to communicate a quantum bit. So that is the advantage of quantum information science in communication. And also in crypto, we have this quantum key distribution protocols that has this information theoretic security guarantee. So the eavesdropper cannot access the information of our key. So that's also an example of this quantum crypto. Okay, and in sensing and metrology, there are more accurate estimation schemes for using this quantum mechanics power. Okay, and also in simulation, we can simulate a lot more complex systems by using some small quantum systems. Okay, so it's natural to ask, do we have any other advantage of using quantum information technologies? So that's our motivations. And we also know that in recent years, artificial intelligence and machine learning has so many applications in theoretical tasks or in more practical application tasks. So there's a question, because AI and machine learning, they are performed using some physical device, some physical computer. What if our computer is now a quantum computer, or a robust quantum computer and large scale one? Then can we do the AI job or machine learning job with this quantum computer? That's our main question. And also doing this is one thing, but can we have some advantage like the one I mentioned before? So that's our central question in this field. Also, to me, I more care about how this quantum information science framework can reinvent the way like we study machine learning. How this quantum information science can provide more insight in this AI and machine learning. So that's our goal. Okay, so firstly, I will briefly talk about the history of quantum machine learning. Okay, so back in 20s, there are actually many literature studying quantum machine learning at that time. However, I wouldn't consider those papers as quantum machine learning studies, because I think they are mostly focusing on the detection and estimation problems. So what are the difference between detection, estimation, and also learning? So if any students you are aware of machine learning, or you take the courses of machine learning, can you say something about what is machine learning? What is the definition of machine learning? Okay, what about learning? So what's the difference between detection and learning? So to me, in Chinese, I would say machine learning, to use one word to describe machine learning is like 学以致用. We want to learn, we want to train, but the main goal is we want to generalize, we want to test, we want to apply what we trained before to some future tasks. So in 20s, there are only estimation and detections. There's no learning, there's no generalization, there's no application of your trained stuff to the future prediction. Okay, so that's the 20 studies. And then in 2013, there are a group in MIT, Seth Lois group. They try to use some quantum computing algorithms to speed up the implementation of machine learning tasks. So they call this word quantum machine learning, but I don't like this word very much, because from this word we don't know anything about what is quantum machine learning. However, but they are a big group, and they propose such a fancy terminology. Okay, so there are a bunch of papers from 2013. Like in 2017, there's a Seth Lois group and a professor in University of Washington. They published a paper in Nature called Quantum Machine Learning, and basically they are trying to speed up any implementation process in a machine learning. For example, like the principal component analysis, we know what is PCA, and then they can speed up this PCA analysis process. Okay, so they publish this paper in Nature Physics. And also the support vector machine, and we'll talk about this later. And this is PRL in 2014. And there's a book by Peter Wittig. I think this is from 2016. So that's the early studies of quantum machine learning. Basically, they are trying to speed up the process of a machine learning. So here, the machine learning I talk about is classical machine learning, but they use quantum algorithms to speed up it. Okay, so, and then there are some judges from 2015 about how to use a quantum computer to do a machine learning task. So firstly, a professor from UT Austin called Scott Aronson, he published a paper on Nature Physics called Read the Fine Print. His goal is to mention that there are still some caveats of doing quantum machine learning. Okay, so to speed up a machine learning task, we may have some advantage. We can save some computational time. However, if you want to prepare the state, then this process might cost very much. I will talk about this later. And also, there are some comparisons between the state-of-the-art classical machine learning algorithms with this quantum machine learning algorithm proposed by the MIT group. They compare all the whole time complexity. So there are certain issues that we want to solve. Okay, and there are two types of these quantum neural networks proposed in 2018. The first one is we call the quantum Boltzmann machine. Boltzmann machine is like a physical process, and then they try to characterize this process using the quantum system. So this paper was published on PRX. This is a very good journal, and I will not go into this detail because it's like more of a physical structure, and this machine is not universal to solve any classical machine learning problems. So the later one is more popular. It's called the quantum feed-forward neural network. It's published on PRA by this quantum circuit learning. I will talk about this later. So these two are the main quantum machine learning tools. So many studies try to modify their framework. Okay, and later there are many papers trying to find implications of those two quantum neural network papers. So, like in this Nature paper, they try. I will talk about this paper later. They try to provide some guarantee that quantum machine learning does help in this supervised learning scenario. And there are several papers to study the capability of a quantum system on doing this machine learning task. Okay, so and there are many papers ongoing. Like in last year, they study what is the theoretical power of a quantum machine learning algorithm. So there are more studies on this field. They try to find out the real power of quantum machine learning. Okay, however, there are certain problems from the classical machine learning because we know that we cannot learn for free. There's no free lunch theorem in the class field. So in classical neural network, we have several problems. Also in the quantum case, we also have those problems. For example, there is Baron-Pertolds. This means that when we want to train our systems, in classical case, we sometimes have this vanishing gradient problem, so we cannot train, it stops, so we cannot, the performance saturated, so we cannot go to train a very well system. That happens in classical case, and they happen in the quantum case as well. So there are several studies try to figure out how to solve those problems in a quantum machine learning algorithm. So there are more studies in this direction. Want to fix a quantum machine learning algorithm, want to train it well. Okay, so there are many studies from in this direction. Okay, so now I will going to talk about what is quantum machine learning actually. Okay, so in this slide, so on the right-hand side, we have these four categories for quantum machine learning tasks, and this came from this paper in 2006. So on the horizon side, we have this data processing device. It's like our system is classical or quantum, and here the vertical side is like what is our data, what is our goal to learn. So the CC part is obviously to learn the classical data from using a quantum machine. So that is basically a classical machine learning task. Okay, so for this QC, it's like our goal is to learn a quantum object by using some classical machine learning algorithm. So our device is a classical learning. So basically here, we want to apply classical machine learning techniques in learning, in solving some problems in a quantum system. For example, if we want to learn a quantum state or quantum circuit, unknown quantum circuit or quantum device, sometimes we need to apply the classical statistical learning theory into the quantum regimes. But it's not naively applying classical machine learning algorithms, because in the quantum setting, we are the system is more complex. We have to deal with lots of matrix stuff. Okay, so in Scott Anderson, he initiated the early studies to learn the quantum state using some classical statistical machine learning techniques. And also I have some papers to generalize his results to learn a quantum measurement or beyond. Okay, and the MIT group from CSLOI, they try to use, their goal is to learn classical data. So we call that CQ because their data set is from classical data, and they want to use quantum computing algorithms to speed up the classical task. So they fall into this category. And finally, the QQ part is try to learn a quantum data with quantum machine. However, this direction is largely open because what do we mean by quantum data? What do we mean to use a truly quantum learning algorithm? So this part is like still open. Okay, so that's the basic crisis of this the intersection of quantum information science and machine learning. However, I will have different definition for that. I will more detailed definition for that. So before that, let's first recall what is a learning framework. So now we can see very detailed what's the difference and where the quantum part can come in. Okay, so for conventional learning framework, we have a target to learn. So that's our goal to learn. So we denote this by an unknown target function, which may be a function from x to y, and x and y can be very abstract. And the target function will generate some data. We call this a training data set. And they come from this target function, and then maybe generated from some unknown distribution, but we don't know what is the probability law under it. Okay, and a learning algorithm is to use the training samples to pick a possible, we call the hypothesis, which will approximate or target in certain sense. So that's our learning algorithm and the hypothesis set do. Okay, so we want to propose the final hypothesis. The final hypothesis will approximate our unknown target in certain sense that if we apply our final hypothesis on future data, they match almost. So that's our goal for learning algorithm. Okay, there are many directions and many scenarios. If like the supervised learning, our output set is like can be like a binary set, so it corresponds to a binary classification problem or a multi-class classification, or the output set can be like continuous range, so it's basically a regression problem. Or the output set can be empty, so basically it's like that unsupervised learning. So this framework captures most learning scenarios. Okay, so how can we evaluate our final hypothesis? Firstly, because we have these training samples, we can calculate we call it empirical loss or empirical error. However, our goal is to make our empirical error to approximate the ensemble error as much as possible. However, we don't know the unknown distribution at the top, so here we cannot calculate this unknown ensemble error exactly. However, if we have a good hypothesis set and a good training algorithms, this training error will be very small. Furthermore, if the data set is good enough and also the hypothesis set is not too big, from some theoretical statistical learning theory, it guarantees that the empirical training error will approximate the testing ensemble error. So that's the spirit of a learning framework. Okay, so keep this picture in mind. That's the main, the whole idea of the learning algorithm. If we divide these blocks into several categories, so we can really see where the quantum system can come in. Okay, so right now see the left part, the unknown target and unknown data. We can define the goal of a learning task by their data and goal. For example, what is the goal we want to learn? We want to learn classical data or quantum data like quantum state or quantum system or quantum circuit. Okay, so from this data and goal, we can define this category as classical or quantum or hybrid. Okay, so from here, we have the data and goal, they are classical or not, so we have some categories. Okay, the second part is the learning algorithm. So our learning algorithm, I will call that more precisely as the learning mechanism. What is the learning mechanism you want to apply on a task? Is it classical or is it quantum? For example, in the K-means clustering problem, we want to define a new sample into some categories. So we'll compare the center point and calculate distance to see which class it belongs to. And however, this scenario is like a classical comparison, so it is only a classical comparison mechanism, so it is not quantum at all because there is no quantum part. So if we use the learning algorithm, what is the really classical part or quantum comes in this learning mechanism determines how we will define how we will categorize this set. Okay, finally, if we want to implement the learning mechanisms, then we can think about we want to perform it on a classical device or a quantum device. If we want to perform it on a quantum device, we may need to design some circuit level algorithms so that we can code some quantum gates to perform these learning mechanisms. So finally, we can see if the physical device we want to use is classical or quantum. Okay, so roughly speaking, there are classical quantum, classical quantum, classical quantum. There are basically 8 different categories for the whole learning framework. So like classical, 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 the classical learning, or the classical, if you want to, the learning mechanisms is like a classical algorithm, but you want to use your quantum computers to speed up it, so it's like a MIT group. Okay, so there are many different categories, and in this talk we'll mostly focus on these 2. The data and goal, they are classical because we want to do some quantum advantage on some classical problems, and then we'll talk about the learning mechanism is classical or not, and also the physical device is quantum or not. Also, and there are actually other categories, but I will not talk about this in this talk. And also, there are certain research problems that still open in a fully quantum learning scenario. Okay, so first, the data and goal, they are fully classical. We want to try to use a quantum device to run the classical data, and the data are all classical. And also, we want to use just classical learning mechanisms. So that's the early studies from the MIT group. Okay, so before going light, I will first review how is the quantum learning can do a classical job. Okay, so because now our goal and the data, they are all classical. So basically, we want to feed in our classical data set into our classical learning machine, and then we will make some prediction. That's the goal in the classical case. In the quantum case, because right now our data set is classical, but we also feed in the classical data into a quantum machine. So eventually we will have some encoding process so that our quantum machine algorithm can recognize the classical data. And because our goal is to make some future prediction on the classical data, so we have to read out, make some measurement to read out our prediction. Okay, so this process, if you took the course from Professor Guan, so we know that we can this part can be easily done by a quantum system. We call this encoding the state preparation process, and this quantum machine learning algorithm can be performed by some quantum evolution, which are some quantum gates and unitaries, and then we make some measurement to read out our prediction, our data for future prediction. So this is like a natural implementation by a quantum system. Okay, so here we have to do some state preparation. So here there are many encoding methods, and they will affect the efficiency of a quantum machine learning algorithm. Okay, firstly, I'll talk about this information encoding, and as I mentioned before, we call this the state preparation in a quantum machine learning algorithms. So in the training phase, we have a bunch of data, x1 to the xm, each are an n-dimensional feature vectors. So there are many methods being proposed to do this data state preparation process. I will just talk about the basis encoding and the amplitude encoding method. Okay, so to give you an example, assume that we have this xm data set. Each xm is an n-dimensional vector bit string. Okay, here they are bit strings. So if our data already come from this bit string, so it is very easy to encode it into a quantum state, because we just use a computational basis state to capture each bit. So it's actually very easy, and we make a superposition for all the data set. Then we can fit in this quantum state into our quantum circuit. Okay, for example, if we just contain two data like 0101 and 1110, and then the data set is like a superposition like this form. And here, when I mentioned about this cat vector, I made their tensor product. So it's easy to calculate. It's like this vector in the Hilbert space and this one. So I will not go to the detail because they are very easy. So our data set is like this form, and then we can apply some unitary gate to infer or to process this data set. So for this basic encoding, the preparation time is like big O in M and N. M is like the number of data sets, and N is like the dimension of a feature vector. So here, unfortunately, the preparation complexity is high, is linear in the dimension, also in the number of training data. And then the MIT group, they proposed a method called quantum random access memory. They can speed up this process to log n, so it's an exponential speed up in the dimension. Okay, so QLearn is basically to load your data from superposition state into the second registers. And this process is a unitary, so in principle they can be performed in a quantum computer, and they proposed this method in this PRL paper in 2008. However, this is in principle doable by a quantum computer, but an efficient hardware, like to use some gate, to use as few as possible gates to implement such a QRAM is still open. Okay, so right now many quantum machine learning studies, they assume that we have this QRAM to do the state preparation job, and then we can do the further training. However, how to implement this on a physical device, efficiently implement it, is still unknown. Okay, because we know this is a unitary operation, but we don't know how to use some efficient gate to implement it. So that's the problem of the basis encoding. And you may wonder, if we do have a QRAM and we do have this basis encoding, and how can we speed up using this basis encoding? Okay, so the idea is very simple, as called the quantum parallelism. So I will not go to this detail, but by using this quantum parallelism and superposition, we can read all the data and our input-output pairs into our first register and the second register. So in one query, we do have all the information contained in a quantum state. So we can try to design some unitary to infer some hidden structures or trends in these input-output pairs, because all the input-output pairs, they are stored in a superposition by just one query. So that's quantum parallelism. Okay, and by perform some measurement, we can read out these input-output pairs. However, if we do want to read out every input-output pairs, it's expensive because we want to make so many measurements, and the measurement exponentially grows. Okay, so yeah, to caveat using this basis encoding, the first one is that we need to use very large amounts of qubits, because if your data set has very large dimension, then we need to use so many qubits to do it, because we have to use this basis encoding, and also how to realize the QRAM. And the first question is that is why we want to invent a very large scale quantum computer. Okay, and the second one is called the amplitude encoding. Assume that our feature factor that has very nice structure, like they are normalized, also the sum of square equal to 1, we call it normalized. And you can also consider other scenario, but it's actually not expensive to reduce to this to transform our data to satisfy this condition. Okay, so if our data set has this nice structure, and then we can only use log n qubits to encode those data set in the quantum superposition state. So basically, we just encode all the data entry to the probability amplitude of a quantum state. And then we only need to use, because there are exponentially many amplitudes, so we only need log n qubits to encode all the possible feature entries into the probability amplitude. And then we superpose any data in the data set to our superposition state. Okay, so in this case, the state preparation time also is linear in the numbers of training data and also the dimension n. And then by using the QRAM, and if our data set has some nice uniform structure, then the state preparation can be easily done by the QRAM. Okay, so let's assume that we do have such an amplitude encoding in this superposition state. Then how can we do about it? How can we further train from it? Okay, so I will use this clustering problem as an example. So a clustering problem is like to classify testing data, which is just an n-dimensional vector, into two groups. Okay, so there are phi and w. There are two groups. And in the classical case, the best way is to compute their distance in certain norm, for example, to compute the new data set and the center of one of the group. Okay, to compute this distance, it's inevitable to calculate each entry. So the dimension actually matters here, because if you want to calculate norm, so the data set and also the dimension matters. So in the classical case, you have to take poly time in m and n. So that's the best you can do in the classical case. Okay, because you have to evaluate the inner product, and when the dimension is large, you take linear time in the dimension to calculate this inner product. However, in the quantum case, if we do have this amplitude encoding, we do have this quantum superposition contain all the data set, then we can use some like swap test to calculate the inner product. And this calculation is dimension free. This swap test holds regardless of how many qubits you are for this psi and phi state. So the dimension vector does not matter in this swap test. So that's the central idea in Sage Lewis early studies in quantum principal component analysis, because dimension vector is not important by using this swap test. So that's the advantage of using the amplitude encoding and also swap test in speed up a quantum clustering problem. Okay, so in a quantum case, they can speed up the computational time by this log n. So it is an exponential speed up, provided that you have an amplitude encoding. Okay, I will also talk about the drawbacks of this method. Okay, so here we have to measure the amplitude. We'll have to read out in the end. So here, if we want to read out every possible entries, then still we have to the computational time is still a lot, because there are exponentially many probability amplitudes, and you need exponentially many measurements to read out each entries. However, in some problems, if you don't want to read out every entries, then you may save time. So that's the one thing we have to be careful in this amplitude encoding strategy. Okay, and like I mentioned before, here we need a QRAM to prepare the superposition state in amplitude encoding. However, if our data set is not very uniform, then it may consume large of computational time to do the amplitude encoding, even in the QRAM case. So there are papers, these two papers were discussing these issues. If you spend too much time in the state preparation process, then even if you have this exponential speed up, later on, then the whole process takes exponential time. So there's no speed up anymore. So in this state preparation, you have to be very careful, and it also depends on your data set. So that's a very crucial part we need to keep in mind. Okay, so the next one, I want to talk about this support vector machine with QRAM. And this is a very famous classical machine learning algorithms from the 90s. And basically, the goal is to do some quadratic optimization problem like this one. I will not go to this detail. But the thing is, to do a support vector machine, you have to calculate some kernel function, because they are kind of to calculate the inner product between each data set. And in the classical case, we do have this polynomial time in the number of data and the dimension. However, if you use a quantum algorithm with QRAM, you can speed up the process by from this poly n to log n. So it's an exponential speed up in dimension. And the idea behind it still to use some quantum algorithm techniques and superposition, but I will not talk about the detail. But it's, in the end, they found that there are quantum algorithms to speed up the whole thing from poly mn to log mn. So it is an exponential speed up. However, there are still drawbacks in this scenario, because we will use QRAM here. So they use the QRAM and also some solving the linear equation methods called the HHL algorithm from Aaron Harrow and Seth Loy, and also Hazadi in 2006 in the PRL paper. However, in this paper, they mentioned that if we want to do such a solving a linear equation, the matrix describing the linear equation must have some nice condition number. If they have very bad, the scales very bad, then the algorithm still takes lots of time. Okay, and also the QRAM is needed in this support vector machine, because you want to prepare all the data in a superposition state. So provided that you have a QRAM and the data set scales very well, then you do have an exponential speed up. But how to efficiently implement and QRAM is still an open problem. So the whole scheme was presented in the 2014 paper to speed up a very important classical support vector machine algorithm. Okay, so there are researchers start wondering if we want to do QRAM, can we speed up a machine learning task without QRAM? So that's the next slide. So here, the basic idea is that we don't want to use some QRAM to superpose all the data in a quantum state. Can we still apply some quantum features to do some support vector machine the task? So they call this the quantum feature space method. What is like? So for every classical data, they will encode this data. For each data, they will map this data into a high nonlinear dimension space. So they will transform it into some high-dimensional Bragg sphere. For example, let's just take one cubic case. If we want to classify this line into two categories, the red part and also the blue part in the middle. Okay, so in the classical case, we can just use a linear classification to perfectly distinguish these red and blue lines. However, we have to use some quadratic classifiers to do this classification. But in the quantum feature space, they can do some nonlinear transform to map this line back to a Bragg sphere of a qubit. So in the Bragg sphere, it's like the red part maps to this part, and the blue line is like this part. So we can perform some linear classification to perfectly separate. So that's the basic ideas. To use the exponential large space, Hilbert space, behind the quantum system to do the nonlinear feature transformation. Okay, so they propose some mapping method they call it ansatz, and then for each classical data, they can do this nonlinear mapping for one qubit case to two qubit case, and also more general case. So they can do this we call feature transformation to map each data back to a large Bragg sphere. Okay, and behind this, in this large sphere, they can also do because they want to do a support vector machine, so they can also calculate the kernel, and this can be done by some inner product of qubits or your quantum states. Okay, in certain examples, calculating kernel function in a support vector machine is hard because essentially you want to do some inner product and the dimension factors come in. So now if you have a quantum feature factor, then they show that there are some certain quantum speedups for calculating these tasks. So they are real quantum speedup and without amplitude encoding. And they perform this kind of idea in some superconducting 2 or 4 qubits processor, and then try to classify such an example. So there are many like red part and blue part, and you have this turning point, the Bragg dot and the white dot, and then they transform like a very complicated graph into the just two qubit superconducting processor, and then that's the down part. The Bragg dots are like on the left part, and also the white dot on the left part, so they can easily separate it. But it's not perfect. However, it's not separate. It's not perfectly because the data is kind of complicated. But they can do this job only on a 2-qubit superconducting process. And the reason is that the quantum Hilbert space is exponentially growing. Okay, so they use this idea and then test their idea on a superconducting device. So they propose this paper on 2019 Nature. Okay, so that's the idea to implement a support vector machine without QRAM. Okay, and if you are interested in such a topic, then you can play with the IBM Qiskit. There are also many toolkits to perform the quantum SVM. Okay, so the next part is to learn with the quantum machine, because previously their learning mechanisms are all from classical, like support vector machine, like the K-means clustering, they are all classical. But here, can we transform the learning mechanism into a truly quantum system? So that's our second part. And our physical device will not consider classical part or quantum part. By the classical part, I mean to use some simulator on a classical computer to simulate the whole process, because right now we don't have a really large scale quantum computer yet. Okay, so in 2018, they proposed this variation of quantum circuit structure. The idea is to parameterize the quantum circuits. They are basically just unitary matrices. And then we can just choose some, for every unitary matrix, we can just use some rotation gates to present it. And then we parameterize every rotation gate by some parameter theta 1 to theta n. So then we can parameterize the whole quantum circuits. Okay, then we can perform some measurement to read out our answers. So let me use this picture to present the idea. Here, we'll first use some state preparation, the state preparation process to encode our data into some circuit Vx. There are a bunch of unitaries. And then we'll perform some weighting matrix. Weighting matrix is like just the classical neural network ideas, but then we'll use a quantum gate. We use a bunch of quantum gates to represent those weighting matrices by a large unitary gate. So given every data, we'll calculate the parameter to find which combinations give lower loss. So that's the idea of this variation of quantum circuits. And we make some measurement to read out our objective functions. So here, given every input, and then the final hypothesis is parameterized by some data, and the whole objective functions came from a quantum system. So that's the idea of this variation of quantum circuits. Okay, but right now we don't how to really implement such a variation of quantum circuit. The main idea is to use some hybrid method. Okay, so we will use quantum machine like the formula presented before to compute an objective function of a given data, and then we can calculate a loss function by using some classical device, because that's kind of more efficient to use a classical computer to compute the loss. And then we will calculate some gradient. I will talk about the gradient later to find which parameters may have the better loss, and then we will feed in those data into the quantum circuit to obtain the next round of the objective function. So the idea is like this. We will try to find which parameter set optimize our objective function. So for each data, we will compute an objective function at time t+1, and then we will use a classical device to find the gradient, either by some analytical form of gradients or some numerical gradient methods they are well known in the classical case. And for example, you can use some Python tool like PyTorch to compute the gradient to find the next round parameter. And then we'll feed back this parameter set back to your quantum circuit to parameterize your circuit again. Then we can compute the objective functions. We call such a scenario a hybrid training for VQC. Okay, but there are actually many optimization methods, but they are all classical, so we can use some classical methods. And there are like this QAOA, heuristic quantum algorithms, to calculate, to do the optimization task. And then there are also some gradient-free, we call a particle swarm optimization tool. They are all from classical. So we can actually try different optimization methods to minimize your loss. Okay, and also there are numerical ways to calculate difference, and there are also people discussing it. We call the finite difference method. Then also in the 2018 paper, the novel thing is that they can provide an analytical way to calculate the gradient of a VQC. They call it parameter shift rule. What is that? So in general, our rotation gates, they are unitary. That's fine. We can perform it on a quantum computer. However, the gradient of a unitary is no longer a unitary in general, so they cannot be implemented on a quantum computer. That's kind of a pity. However, they find a way, because they are all like rotation gate, they found that those gradients can be decomposed as a linear combinations of unitaries. And there are a bunch of unitaries who can perform the unitaries on a quantum computer. So essentially, we can calculate the analytical form of the gradient by a quantum circuit. So they can do this job on a quantum circuit, and then they will use some. Once they got this gradient, they can use some classical optimization rule to find what is the next round of the parameters. So that's the novelties of this quantum circuit learning paper. So this kind of convenient. Okay, there are other more fancy gradient methods published on the quantum journal. They call more higher order gradient methods. Okay, so in the Qiskit tool, you can also have many optimization package for you to conveniently calculate this hybrid optimization process. And also in this PennyLane is by a company called the Zapata in Canada. They propose some quantum machine learning tool, so you can run the whole thing like I mentioned before by yourself. Okay, so how to really parameterize a quantum circuit? There are actually many ways. We call how to choose a good answer for a problem. Okay, so the idea behind a variation of quantum circuit is that we only use, because we know that the circuit, if we have a bunch of qubits, the hidden dimension is very large, exponentially grows. However, the parameter we want to